Every aircraft is designed to carry out a mission. The main reason for developing this aircraft is to carry avionics and UGV. As a result of some technical calculations, we decided that the structural and performance parameters of Kesekci should be as you can see on the screen. High-end production methods are used while producing this aircraft. As it is known, rib and spar matrix structures are used in the aircraft's fuselage. We produced most ribs from birch plywood using carbon dioxide laser cut method for more precise production. We applied carbon coating to some ribs where more durability is needed. Furthermore, all aircraft surfaces are made of carbon fiber with the vacuum laying method. We have obtained a light but robust surface structure thanks to this method. The avionics system is divided into two parts, according to their power consumption to minimize the magnetic field effects created by high power elements. As you can see, while the first subsystem consists of the engine, ESC, and first battery, and they are placed on the front side of the UAV, the second subsystem contains the remaining and comparatively sensitive avionics, and they are placed on the rear side of the UAV. The aircraft system has 4 different communication systems with the GCS, as seen on the screen. 3 of them will be used with Wi-Fi 5 GHz, RFD 900 Hz, and Futaba 14 channel 2.4 GHz aircraft system, and the DigiXP3 Pro will be used for communication between rover and GCS. We are attempting all of the missions. We have high confidence in succeeding them except for the drive to location task in the airdrop mission, because after the impact, the solars of the UGV have a potential to break, and the system would not drive itself, but we find its possibility low. We know that developmental testing has a vital role in carrying out a project, so we tested our system unit by unit and kept safety as a priority while doing all the tests. We tested our units for specific reasons. For example, making wing loading tests for every single wing that we produced for 3G to be certain that Kesekci can turn 60 degrees of roll safely. We tested the range of communication elements not to have communication losses in the competition. We tested the GPS accuracy and noticed that carbon fiber surfaces cause inaccuracy on it, so we placed both of the GPS modules 5 cm above the wing. The algorithms developed are first tested on the simulation environment. When they worked correctly, we tested them on our old pre-made frame called XUAV Talon. After making necessary iterations, we tested them on Kesekci. We have a checklist before the flight that includes significant parameters for a safe flight. For example, whether the propeller direction is correct and the CG of the aircraft is in the right place. You can see that our team checks all the safety measurements before takeoff. Autopilot controller parameters need to be tuned for an autonomous flight. Autopilot uses PID, L1, and Total Energy Conversion System controllers to provide autonomous flight. These 3 controllers have been tuned in the aircraft's first flights, and their response to the desired behaviors has been improved. In addition, the takeoff and landing tests required for autonomous flight were successfully carried out. In addition, the aircraft is commanded by the ground control station developed by METU ANATEK, specifically for the AUVSI SUAS competition in the tests and the competition area. We tested the range of the communication equipments we use and obtained the results given in the table. The results show that our communication avionics are sufficient for secure communication in the competition area. L1 and text controllers tunings are very important to reach a high waypoint accuracy. The team calibrated those controllers for Kesekci and tested them accordingly. Also, the Waypoint Radius is an important parameter for this mission. This parameter is determined as 15 feet by the team to achieve high waypoint accuracy. We tested those parameters in the gazebo simulation environment, and you can see the test results on the screen. Those tests were also conducted in real life by Kesekci UAV, and the results are close to the simulation environment. These results ensure that we have self-confidence in the waypoint accuracy task. An algorithm was developed for the obstacle avoidance task using the Python Shapely library. This algorithm ensures that the routes avoid obstacles at a distance determined by the team. This algorithm was first tested using the Python matplotlib library. Obtained routes were observed using this library, and improvements were made accordingly. You can see the sample routes on the screen. At this stage, 92 different routes were tried, and 79 were successful. Then, tests and iterations continued using gazebo simulation. During these tests, 54 of the 58 stationary obstacles were not passed. Finally, in the test performed using kasetçi, 22 of the 24 obstacles were not passed. Overall results show that our obstacle avoidance algorithm can achieve the task. For mapping and object detection missions, kasetçi UAV has one baseless industrial camera. You can see the characteristics of the camera on the screen. We did some image performance tests with this camera, and examples of camera images taken from 130 feet and 200 feet are as follows. Our imaging system can be used very automatically thanks to the superior features of the camera we prefer. Therefore, a concise procedure is sufficient for our imaging system to be ready. The pre-flight camera calibration procedure is as follows. Firstly, adjust the camera aperture according to the amount of light and the environment. Secondly, place an object 40 to 60 meters away and adjust its focus until the camera shows that object clearly. Thirdly, set exposure to auto. Baseless auto mode provides good exposure by constantly controlling ISO and shutter speed. Lastly, enable automatic white balance and generate lookup tables. Object detection, classification, and localization is done in 3 steps: autonomous region of interest detection, manual classification, autonomous localization. To test our performance on the ODCL task, we have printed 30 different objects and scattered them in the fly zone. The test results are shown on the screen. The results clearly indicate that we have confidence in object detection, classification, and localization. Mapping algorithm tests were done unit by unit. We carried out our tests in 2 parts, simulation and real-life basis. In the tests done, navigation and image stitch unit tests were conducted, and then the full mission test was performed. High success rates have been achieved in navigation tests, and the system is made more robust with the improvements made in image stitching. 4 maps were successfully generated in the full mission tests. Thanks to the filters we use, the map projects accurately. Eliminate error improvements are continued by adapting filter methods for minor stitch errors that occur in some maps. In the technical design paper, we have stated that we are preparing for the airdrop mission and have designed a UGV specifically for it. It had to fall on 2 surfaces to be able to navigate, so we have made a few changes to the design to increase the likelihood of it falling in the direction we want it to fall. We designed the wheel as a semicircular section. We also increased the area of the surfaces we wanted to fall. Thus, we made it possible to drop the UGV on the desired surface. 9 airdrop tests have been carried out, and you can see the results of them on the screen. UGV was used in 5 of these. As a result of all these tests, we can say that we are in an assertive position in the airdrop mission. To accomplish the full mission, we created a virtual environment of the competition. We defined a region similar to the competition area, located the letters we printed before, and drew 11 to 12 waypoint routes with some random obstacles. Also, we created a mapping area and pointed at an air delivery point and drew circles around it by decreasing the accuracy point. We checked the printed letters and air delivery's location by using mobile phones to measure the accuracy. We also simulated the flight line with the team crew. We have 3 ground control stations, 1 pilot, 4 groundsmen, where 3 of them are mechanical crew members and 1 of them is an electronics crew member. Our preparation time is below 15 minutes before starting flying, which obeys the rules. Using our ground control software, we started the full mission by landing. kasetçi first followed all of the waypoints by order, then went to the air delivery location and dropped its payload. Then it went to the mapping area and started its route. While going through a mapping route, it captures the printed letters on the ground. It sends them to the ground station and the crew sends them to the interpolation system after doing the necessary labeling. When we attempt the full mission demonstration, we have seen that the overall grading is not different from our unit tests. As seen on the table, we are not going to submit the ODCL objects autonomously, so we don't expect a point from there. In addition, our drop accuracy mean error is 11 feet, and since we get full points if it was 5 feet, we expect 50% points from the drop accuracy. When we sum all of the points we got, we have seen that our expected mission demonstration point is 79.6%. Thank you for your attention. Greetings from the METU ANATEK team.